Okay guys, the next quantities I said we are going to talk about is the pitch factor, distribution factor, and turns per phase. What I want to first talk about is the I want to talk about the sorry is the pitch factor. Okay. The nice thing about N5 is that the pitch factor, it's always given. That is the nice thing about it. Okay, but a pitch factor is basically based on let me just put this down. Let's say you have a wire, yeah, 1/10. If you make 1/10 of this wire, you end up having two conductors, one conductor, second conductor. So basically 1/10 of wire is equivalent to two conductors. That most stands for conductors. So 1/10 of wire is equivalent to two conductors. So if you see this 10, let's say I make a loop this wire. This wire has this side, this side, this side, and this side. So the distance between the sides of a loop, we call it a coil pitch. The distance between the sides of a loop, or a 10, this side and this side, this side and this side, we call the distance from this side to this side, we call that a coil pitch. Then let's say we have poles, we have magnets, north and south. The distance between one pole, let's say we have, okay, let me put it like this, sorry, north, okay, sorry, south. Okay, if you look at here, we have how many poles do we have here? We have 4 poles, meaning we have 2 pairs, north and the south, north and the south. Okay, and the distance from the center, listen, from the center of one pole to the center of the adjacent pole, that we call it we call that a pole pitch. Always remember that, guys, or a pole arc. The distance from the center of one pole to the center of the adjacent pole. Okay, so when okay, listen carefully, when the coil pitch, okay, which is the distance between the sides of a loop or sides of a 10, when the pole pitch is equals to the coil pitch, sorry, the coil pitch is the distance between the sides of a loop, or the sides of a 10, is equivalent, when it is equal to the pole pitch, we say that the coil is full pitched, guys. We say that the coil is what? Full pitched. And they will tell you the coils are pole pitch. When they make that statement, they are basically telling you that Kp, which is the pole pitch, is equals to 1. It is equals to 1. When the coils are full pitch, it simply means that the coil pitch and the pole pitch are equal, and Kp will be equals to 1. Okay, if they didn't tell you, maybe they will give you the value of the pole pitch and say, I'm making an example and say 0.5. But in most cases, they always say full pitched, meaning Kp is equals to 1. Okay, that's it about pitch factor. Please learn on your textbooks how to define pitch factor. It's very simple to define. It is the ratio of the actual EMF that is generated to the EMF that will be generated if the coils were full pitched. Okay, now let us move on to the distribution factor, which is Kd. The distribution factor, guys, it will always be given at N5 level. Okay, but let me just explain what the distribution factor is. Okay, the distribution factor is simply the distribution of the coils or the distribution of the conductors in the stator. For example, I said the stator has slots. I said the stator has what? Slots. I'm putting circles just to represent that they are stator slots. So if all the conductors are concentrated, in one slot, okay, all the conductors are concentrated in one slot, that is unevenly distributed. But if the conductors are distributed among the slots, that is evenly distributed. And when all the conductors are concentrated only in one slot, it means Kd is equals to 1. But if they are evenly distributed, you'll be given Kd. Okay, moving on to the turns per phase. Tp is the what? It is the turns per phase. Turns per phase is equals to, remember we said 1 turn is equivalent to 2 conductors. 1 turn is equivalent to 1 conductors. So it turns per phase, sorry, let me just take out my side notes. Turns per phase is calculated as follows. Okay, Tp is equals to Zp over 2. Zp, guys, is the conductors per phase. And another thing you should be aware of in this topic, per means division. Per means what? Division. Per means division. Okay, so it is Tp is calculated as Zp over 2. Okay, in most cases we will want to calculate Tp, which is the turns per phase. How do we calculate that? We first calculate Z. You can calculate Zt. Zt is the total conductors. Zp is the conductors per phase. That is why we put the P there. Zt is the total number of conductors. You can use this formula where Zp is equals to the number of slots times the number of conductors per slot. Why are we timesing by, why are we saying number of slots times number of conductors per slot? It's because if I do this multiplication, the number, sorry, if I perform this multiplication, the number of, the number of slots and per slot will cancel. Then I'm left with Z, which is the total what? Conductors, which is the total conductors. Okay, which is the total conductors. And as I've said, this, sorry, let me use the right one. Don't know. I need to get new markers. This is, I've said it is the conductors per phase, meaning this is ZP is Z divided by the number of phases. Normally we talk about 3 phase, but if you talk about single phase, you know we only have 1 phase in single phase. But as I've just mentioned here again, a pair means division. That is why I'm saying ZP is equals to Z over number of phases, because ZP is the conductors per phase. Okay, please take note of these formulas that I'm writing down here. I will send a PDF of these formulas or these notes that I'm using. Okay, then the last formula we are going to look at is another way to calculate ZT is to say ZT is equals to, which is ZT is the total number of conductors we set, is the number of slots times 10 per coil times number of layers. Immediately the question will normally say double layer. Where it says number of layers, you put 2. Where it says number of what? Of layers, you put 2. When it says double layer, it will say we have a double layer winding or triple layer winding, we put that number. Okay, number of layers. Okay, number of layers. Okay, then we are about to tackle some calculations, and I'm thinking of going the example approach, because what I normally do with my students, I always tell them as a lecturer I will only go through the examples on the book, then the activities I allow you. I don't want to deprive a person for a chance to be active in class. So the activities, if you have any question on, maybe you're doing a question on an activity or on the worksheet, you may ask. Then if I say okay, it's challenging, I will do a video for that particular question. But for what I will do now, I will do a couple of examples from the textbook. But before I do that, normally this equation, you see this equation, it is not written like this in the formula sheet. It is not, the EMF equation is not written in this formula, in this format. It's the same formula. It is a correct formula. There's nothing wrong with the formula. It's how they are expressed differently. They are just only expressed differently. In your formula sheet, you'll see it as written as EP equals to 2, 2, 2, F, flux, Z, P, K, P, KD. The only difference between this formula and this formula is that you don't need to find TP here, you just find conductors per